Hello learners, welcome back to my channel Shraddha's Physics. In this part we will see the classification of the orbits on the basis of its energy. So from the previous discussion we have already concluded that the total energy of the system when it will move under the action of the central force, then the total energy equal to half mr dot square plus some effective potential. So let us write the total energy of the system, the total energy of the system moving under the central force, moving under the central force, let me write moving under the action of central force is given by E equal to, that is the total energy equal to 1 by 2 mr dot square. This m means the reduced mass of the system, so 1 by 2 mr dot square plus L square divided by 2 mr square plus V. Okay, so here L represents the total angular momentum and that is equal to 1 by 2 mr dot square plus V prime, where this V prime equal to V plus, or let me write L square by 2 mr square plus V. Okay, this is known as the effective potential. This is the effective potential. So if you will consider the attractive potential or the attractive force between the two particles, so if you will consider, let the two particles interacting gravitationally. Okay, gravitationally means here gravitationally. So gravitationally means the attractive force between them is gravitational force. Okay, so in that case, or it may be the any force that will obey the inverse square law. So here the two particles are interacting gravitationally. So for that we can write V will be equal to minus gmm by r. You know, this is your gravitational potential, or this is simply can be written as minus k by r, where k equal to constant, k is the constant, and the negative sign indicates force is towards the center. Force is towards the center. Now if I will put this value in this above expression, that is let me give the equation numbers. So this is the total energy, suppose equation 1, the effective potential, this is suppose equation 2, and here this one is suppose equation 3. Okay, now if I will put the value of equation 3 in equation 2, now we can write the effective potential. So therefore the effective potential energy can be written as V prime equal to L square by 2 mr square minus k by r. This is suppose equation number 4. Okay, now here we are going to plot a graph between the potential energy, that is V prime versus r. So here you can see this, since L square by 2 mr square term, since this L square by 2 mr square is always positive, so V prime can have positive or negative value, because you can see here from this equation 4, since L square by 2 mr square is a positive term, when it has a positive value than that of, it has a higher value than that of your k by r, then this V prime term will goes positive. But when this L square by 2 mr square value is less than that of your k by r, then this V prime value will goes negative. Okay, so here the graph we are going to draw. So the graph between the potential energy versus r. So here the graph or the curve shows the variation of graph, so the variation of L square by 2mr square with the r, and next minus k by r with the r, minus k by r with r, and also here we will show v prime versus r. Okay, now let us draw the graph. Now here you can see the graph that is here. This is this one. This is the potential energy, that is effective potential v prime, that is the black one. It will represent the effective potential curve. Here the graph is plotted between v prime versus r, and here this blue one, it will represent minus k by r versus r, and this pink one, it will represent L square by 2mr square versus r. Okay, and here the energies levels are like E1, E2, E3, E4, you can see here. And here for this line, the total energy here is 0 suppose, and above this line the energy will be positive, that is the total energy will be positive, and below this 0 line this total energy here will be the negative, that is E3 value is negative and E4 value is negative in nature. Okay, so now let us take the first case when the energy is totally positive in nature. That is, this is the case when this total energy, that is E1 suppose, it is greater than 0. So in this case you can see when the value of r, this is the value of r, that is this graph, it is the versus r and here v prime. When this value of r, it will decreases, that is when we will goes towards this center. So when the value of r decreases, so what will happen? So the v prime value, it will increases. You can see the value of at this point, the value of v prime is this much, then at this point this value is this much, and so on. It will goes on decreasing when the value of r decreases. So between this point, so you can see in between this path, when the value of r decreases, the value of v prime increases, and it will increase till it becomes the value at E1, that is suppose at this point A1. So the total energy here, it will be in the potential form, because the kinetic energy at this point will be 0. And here you must keep in your mind that the particle cannot move closer than this distance r, that is r1. Okay, that is when the kinetic energy of the particle, it will reduce to 0. So the particle cannot move closer than that of the r1, and this point is therefore called the turning point. So the for all the points that is situated on the right of A, that is at this path, okay, situated on the right of A1, so E1 is greater than V prime. It means that the particle possesses some kinetic energy from this path, or after this A1, that is when we will move from this A1 to in between this distance, the particle will present, they will possess some the kinetic energy. So the particle approaching from the infinity, they will turn from a distance r1 and again go back to the infinite. So the particle move along a unbounded curve, and that unbounded curve is called the hyperbola. And there is only one turning point here, only one turning point. So let me write for the case 1, let me write here. Okay, let me write here. Suppose the case 1, when the total energy E, that is equal to E1 and it is greater than 0, means the positive. Okay, that is the energy is positive, totally positive in nature. So in this case you can write the central force of motion, from the central force of motion, we can write this E equal to 1 by 2 mr dot square plus v prime, or simply we can write 1 by 2 mr dot square, that is equal to E minus V prime. Okay, and here since the kinetic energy that is equal to 1 by 2 mr dot square, it is always positive, positive, that is the negative value of kinetic energy is not possible. So therefore we can write this E minus V prime, that will be equal to positive. So this will be positive when the energy value will be greater than 0. For that case here we are calculating, and here we will write the point at which the radial velocity or the kinetic energy becomes 0. The radial velocity or the kinetic energy is 0 is called the turning point. Is called the turning point. Turning point, that is A1. Turning point, that is A1. So for the particle with energy E1, we have, that is when the kinetic energy is 0, you can see from this expression, that is 1 by 2 mr dot square equal to E minus V prime. When this kinetic energy is 0, then that definitely E equal to V prime. So here we can write the point at which the radial point or the velocity or the kinetic energy is 0, that is called the turning point. So for the particle with energy E1, we have E equal to V prime when kinetic energy equal to 0. Okay, and you should remember that the R value, and here R cannot be less than R1, that is the distance cannot be less than R1 for a particle. So if V prime is greater than E, when V prime will be greater than E, you can see here when the V prime value will be greater than E, so in that case E minus V prime will be negative, that is your kinetic energy will be negative, which is not possible. So let me write here, if V minus V prime will be greater than E, then E minus V prime will be negative, but the kinetic energy equal to 1 by 2 mr dot square, that is equal to negative, which is not possible. That's why we can say the orbit is not bound. Hence the orbit is not bound. Orbit is not bound. That is, the particle will come from infinite, that is the particle will come from infinity, and after encountering the repulsive centrifugal barrier, that is because of the repulsive force barrier, it will return to the infinity. It will return to infinity, or that is called, that is the path is hyperbola. The path of the orbit is the hyperbola, or the path is hyperbola. This one is important. That is when the energy value will be greater than, or that is the positive, when the total energy is positive, that is greater than 0. So for that case the path of the orbit, or we can say the path, is hyperbola. So let me draw. So the hyperbola is just like this. Okay, so here the particle will come from infinity, and because of the repulsive force it will return back to the infinite, and this distance in between these two, so this distance is your r1. This distance is your r1. Okay, and here this path is called the hyperbola. This is the hyperbola. Okay, now let us come back to again the diagram. So now let us see for the case when the total energy of the particle is 0. So here in this case the total energy of the particle is 0 means in this part. Okay, so here when the particle reaches up to the distance r2, that is when the particle will reaches at this point r2, so at this point a2, so what will happen, the total energy it will be in the potential form as in the previous case, so its kinetic energy will be 0, or you can say the particle will now turn back from a distance r2 and it will follow again the unbounded path, and that will be a parabola. So this point a2, it is again called the turning point. It has also one turning point. So when the total energy of the system is 0, so for that case the potential energy it will again plays an important role, or we can say the kinetic energy, since it will go to the 0. Since kinetic energy will goes to 0, so for that case the total energy will become the potential energy. Now let us write the case 2. Case 2. That is when the total energy, suppose E, that is equal to E2 and that is equal to 0. That is when the total energy is 0. Here the turning point occurs. Here the turning point occurs at A2, at point A2, such that OA2 will be equal to R2, and here this is the same case as in case 1. Okay, that is its kinetic energy will goes to 0 and the total energy will become the potential energy. That is the motion of the particle is unbounded and the path is parabola, that is when the total energy is positive, in that case the path is hyperbola, but when the total energy will become 0, so in that case you can say, let me draw, the path will be parabola. So this is the parabola path. So particle will come from infinity and again it will return back to the infinite. So here this point is O and this distance is called the R2 and the path is the parabola. This is the parabolic path. Now again come back to the same graph. So here let us take when the energy will goes to negative value. So in this case you can see when the total energy of the system or the total energy of the particle is negative, that is suppose for this limit, that is this is your E3 energy level, for this point you can see this horizontal line, it will cut this black curve, this one is your V prime versus R curve, this black line. So here you can see this horizontal line of E3, it will cut this curve at the 2 point. One is suppose A3 and another one, let me write, that is suppose A3 prime. So just a minute, let me write, this is suppose this point is A3 prime. Okay, and here you can see the distance from this line is your R3, and let me write this distance for this A3 prime distance, that is suppose your R3 prime. Okay, so basically we can say that, so since there are two points, that is the two turning points. So here because of the two turning points, so the particle, it will follow a bounded curve. Okay, so the path of the particle will now become my ellipse. That is, when the total energy of the system or the total energy of the particle will be negative, it will cut, that is this graph, it will cut the energy line at the 2 point, and that is called the A3 and A3 point, A3 and A3 prime points. So it will follow an ellipsoidal path. Now let us write case 3. When this is case 3, when the total energy, that is E, equal to E3 and that is less than 0. So in this case, the energy line intersects the curve at 2 points. The curve at 2 points. One is A3 and another one is A3 prime, for which the radial distances are R3 and R3 prime. So the motion is bounded, therefore the motion is bounded between these two turning points, two turning points, also called obsidal distances. And the orbits are not necessarily closed, but bounded between the two circles, of radii, that is R3 and R3 prime. Therefore the resulting orbit is an ellipse. That is, if I will show you, so let us draw here. Let me draw here. So this is your circular path. If I draw, one is for your R3 prime and another for your R3. So here you can see, so this distance is your, from the center, this distance is R3, and here this distance is your R3 prime. Okay, now you can see here this ellipsoidal path that is in the red dotted line. So here we can say that the motion is bounded between the two turning point, that is your R3 and R3 prime. If I will consider the two circle, that is suppose having the radius R3 and another having the green one, that is having the radius of R3 prime, when the particle will lies, the motion is in between these two. So here the particle will follow this path, and it is not necessarily the closed one. So now it will follow again this one path. Okay, and so on, like this or any of the possible path it will follow like this. Okay, so basically we can say that when there will be the two turning point, that is here for this A3, for this A3 and this A3 prime. So these are the two turning points when the energy value is negative. So for this, the particle will follow an ellipsoidal path, and it is not necessarily closed, but it will be bounded motion between the two circles. So here let me write the path is ellipse. Okay, so this is ellipse. I have written in red color so that you can guess the red one, it is your ellipse. Now we will see when the total energy, that is E4, that is for this energy E4, when the total energy of the particle, it is equal to the minimum value of the potential energy. So for that case we are now going to calculate. So this is case 4. Okay, so let us see when total energy, that is E, equal to E4, and that is equal to minimum potential energy, that is V minimum. So in this case the energy line meets the curve at the radial distance r equal to r4, or at the point r4, or at the point a4. Okay, for which V prime, that is the potential, has the minimum value. It has minimum value. Therefore we can write, dV prime by dr, that is equal to 0. Since it has the minimum value, we can write dV prime by dr will be equal to 0, or we can write d by dr of the V prime value, we know this is your L square divided by 2mr square plus V, or that is your minus K by R. We have considered the inverse square law of force, and that is equal to 0. Or here, since the derivative of this term equal to 0, we can write this term equal to your constant. Or let me differentiate this term. So that is equal to first minus L square divided by mr cube, and here this will be plus K by R square, and that is equal to 0. Okay, or this term is not constant because you have to take the derivative with respect to r, so this term is not constant. So here you have, after taking the derivative, we will get this much. Or we can write L square, this is just small l, okay, L square divided by mr cube, that is equal to K by R power 4. Since we are taking Lagrangian as capital L, so simply for the angular momentum we are taking the small l. Okay, so L square by mr cube equal to K by R power 4, K by R power 2, and or this can be written as, or R equal to R square get cancelled with this R cube, so 1 remain R equal to L square divided by mk, or this is equal to R4, that is the radial distance. So here this R, that is the R4, it will give a constant value of the distance at which the body will undergo the radial motion when it possesses the minimum potential energy. Okay, when it has the minimum potential energy, so it will follow a circular path. So here we can write, so the minimum value, therefore the minimum value of the energy, minimum value of energy E minimum equal to V prime minimum, and that is equal to, you know, V prime equal to L square by 2mr square minus K by R. So let me first write, this is equal to L square by 2mr square minus K by R, or in this place, that is in place of R, if I will put R4, or that is equal to L square by mk, so that expression will be equal to L square divided by 2m into, in place of 1 by r square, I will write m square k square divided by L power 4. So taking the square 1 by r square, I will write m square k square divided by L power 4 minus k by r. So in place of 1 by r, I will write again mk by L square. Okay. Now this will be equal to, again I can write get cancelled, that will be m k square divided by 2 L power 2 and minus mk square divided by L square, or that is equal to minus mk square divided by 2L square. So after subtracting, we will get minus mk square by 2L square. This is the minimum value of the total energy, or we can say the minimum potential energy value equal to this much. Since here you can see the potential energy is negative, that is the body is trapped into the fixed orbit. So let me write, since it is negative, that is the total energy is negative, or the potential energy is the total energy, it is negative in nature, that implies the body or the particle is trapped, into, let me write the body is trapped, into the fixed orbit, and is unable to leave it, without the supply of energy, from outside, So here the path of the particle is circle. The path of the particle is circle. So if I will draw, so here the path of the particle will be circle and it has the radius r4. So here for the energy, when it is negative, when the total energy is negative, then the path will be the circle, that is the orbit will be circular in nature. So now let me write the conclusion, that is the total energy. Let me write what we have concluded. The total energy, and here if I tabulated it, that is total energy and your conic. So here, when the total energy is greater than 0, so for that case it will be the path of the particle will be hyperbola. And when the total energy equal to 0, then the orbit will be parabolic in nature. This is a parabola. And when the energy is less than 0, then for that case the orbit will be ellipsoidal in nature. This is ellipse. And when the energy value it is negative, that is E equal to minus mk square divided by 2L square, for that case it will be circular in nature, that is the circle. Okay, so this is the main conclusion of this part. Okay, it means the classification of the orbit in view of the total energy, that is on the basis of the total energy you can calculate the shape of the orbit. So it can be hyperbola, parabola, ellipsoidal or circular in nature, that is depending on the energy. That is, when the energy is positive, then it will be a hyperbola. When the total energy is 0, then it is a parabolic in nature. When the energy is less than 0, that is some negative value, then it will be ellipsoidal in nature. But when the energy value is exactly minus mk square by 2L square, then it will be circular in shape, or it will be, the path will be bounded. So this is all about your classification of orbits. Okay, this is all for today. If you have any doubt, can ask me in the comment section. Thank you all.